Every quantum computer in the world has the exact same problem. The machine relies on a dilution refrigerator, a deep freeze chamber cooled to 10 millikelvin, which is colder than deep space. But that imposing metallic chandelier is actually hiding a severe physical disconnect. The actual machine doing the thinking doesn't live inside that freezing chamber. It sits across the lab in a standard server rack, running at room temperature. To bridge the gap between those two environments, the system relies on thousands of individual cables snaking down from the warm external rack into the freezing quantum core. Nobody set out to build it this way. That tangled, massive bridge is a structural limitation that simply became the standard way to operate. Right now, researchers are working with machines that have tens or hundreds of qubits. Qubits are the basic units of quantum information. But to solve complex, real-world calculations, these systems require thousands or even tens of thousands of qubits. This line graph maps out the scaling trap. It plots the number of qubits against the number of control wires. As you can see, every single new qubit requires its own dedicated control wire running from the outside world. Add more qubits and the wiring multiplies rapidly until the physical space is entirely choked off. But the problem extends beyond physical space. Every single one of those cables acts as a physical conduit, leaking room temperature heat directly down into the ultra-sensitive 10 millikelvin environment. A qubit only functions when it remains in a fragile state called quantum coherence. Introduce even the slightest amount of thermal energy, and that coherence instantly collapses. To scale the computer, engineers have to add more wires, but the heat from those required wires destroys the computer's ability to operate.
In March 2026, the company Sequant published a peer-reviewed study in Nature Electronics that effectively bypassed this physical bottleneck. Rather than trying to design better thermal cables, they successfully operated a digital superconducting control system directly inside the 10 millikelvin freezer, right next to the qubits. The sprawling external server rack collapses entirely. The room temperature electronics are shrunk down into a single control chip and stacked directly onto the quantum processor itself. Moving the control logic inside eliminates the thousands of external cables. It cuts off the thermal leak from the outside room and drastically shortens the communication loops between the chips. By placing the control mechanism exactly where the computation happens, the primary physical barrier blocking exponential scaling has been removed. The technology making this survival possible is single flux quantum, or SFQ digital logic. SFQ is a superconducting circuit technology designed to process information at deep cryogenic temperatures. This chart compares the energy consumption of standard control systems against SFQ logic. Notice the massive column for standard CMOS processors. The SFQ logic operates at approximately 4 orders of magnitude lower energy, allowing it to function without melting the delicate quantum core. This approach is proving out across the industry. Just a few months earlier, in January 2026, a company called EeroQ demonstrated a completely different quantum setup that managed roughly 1 million electrons using fewer than 50 physical control lines. The wiring bottleneck is no longer an insurmountable theoretical hurdle. Multiple engineering teams are actively neutralizing the problem from different directions at the exact same time. CQC's demonstration used a 5-qubit chip. That is a proof of architecture. It is not a fully fault-tolerant, production-ready quantum computer. But the scientific community has long recognized that moving room temperature wiring onto the chip itself is an absolute prerequisite for scaling beyond 10,000 qubits. That prerequisite is now met. Crossing that threshold moves the work out of the realm of laboratory physics and into the world of practical data center engineering and infrastructure design. Quantum computing is officially graduating from a distant scientific ambition into a rapidly emerging layer of real-world computing infrastructure. The industries tracking this evolution most closely need processing power classical computers simply cannot deliver. They are running pharmaceutical drug discovery, rendering complex material science, and optimizing global logistics networks. There is also an immediate security threat. Current cryptographic infrastructure relies on mathematical assumptions that scalable, fault-tolerant quantum systems will easily break. Every major transition in computing follows a pattern. A physical constraint is removed. A new architecture is validated. An entirely new class of problems becomes solvable. The dilution refrigerator in the lab is still running. but the scale of computational power that can actually fit inside it has changed completely. With the era of scaling engineering underway, which industry will reach quantum utility first, and which one is completely unprepared for what that reality means?